Okay, this is homework number 4, starting with question number 4. It's basically a simple Kirchhoff's type question. We just started off with defining our directions of current, right? Here we have what's going in equaling to what is going out. There's kind of a little trick I like to do where I start with the biggest battery and then assign the current that would truly be going to that one, and then just go from there. Like I said, it doesn't matter as long as you're consistent, because even if you guess wrong, your current will just come out as a negative, and we know how to rewrite that and adjust the guess. Okay, so I have all my directions. The first part of this is the junction rule. So at A, going into junction A here, we have I1 plus I2 is equal to I3. So that's my junction rule. And the next thing is the loop rules, right? So the loop rules. So I'm going to do 2 loops. You need to have 2 loops to solve any one of these. I'm going to start at the top, and I'm going to draw something that looks like this. Okay? And whenever I draw that, like I want to now label that I'm starting with a loop that's going in the counterclockwise direction. So my loop 1. And I always like to start behind the battery. Starting behind the battery, if the current and the direction of the loop are in the same direction, it's a positive value, right? So what do I mean by that? So like I drew my loop going counterclockwise. So within that circuit, it's going like this, right? And then also within the circuit, the current here is going this way. So because, the counterclockwise and the direction of the current are the same, you write the positive value. So that's an 8. Looking what's next in line there, we have that resistor, that 2 ohm resistor. Because the direction of our loop and the direction of the current here is going the same direction through the resistor, it's minus. So minus 2I1. Keep it moving. We hit the next, like we're like going along here. We now hit this battery. So now our loop is still going this way, but here the current is going this way. So you imagine those like arrows are bumping into each other. You can imagine. And that means minus. The battery is now minus 15. Moving it along, we hit the 5 ohm resistor, and kind of the same thing we just talked about. Our loop is going this way, and the current here is going this way. So because of that, we do adding this time. So plus 5I2. Okay. So now all you need to do is just clean this up and simplify it. And I'll let you guys just do that like addition on your own. But you'll end up with minus 7 minus. No, did I miss a? Oh yeah, there's this 8 ohm right here. And then it would be, again, moving it along here. The current's going here, our loop's going this way, and for those reasons, it's going to be minus 8I1. So then when you clean everything up, you'll have that minus 7 minus 10I1, and then plus 5I2. Now we can do another loop. So you can either do the other loop in here, but that's kind of the way that you always do it. So I'm just going to do the outer loop just to show you how that's done. So I'm going to call this big guy right here loop 2. And again, we're going in that counterclockwise way. So loop 2, I'm going to start behind the 8 volt battery. So 0 equals, and then our loop's going this way. The current here is going this way. So it's a positive 8. And then we hit the next resistor, minus 2I1. We keep moving it down. We hit the 1 ohm resistor. Loop's going the same direction as current here. So it's going to be minus I3, or minus 1I3. Well, same difference. And then, minus to plus terminal, the loop's going the same way. So plus 10. We hit the 3 ohm resistor, minus 3I3, minus 6I3, minus 8I1. Okay, did I get everything there? Yep. And now you just got to clean this guy up, and you'll end up with 18 minus 10I1 minus 10I3. Okay. So now we're going to need to clean up our junction rule equation so that we can solve for everything in terms of a single variable. So let's get that I3 to the other side. So minus I3 equals 0. So we don't know anything about what I2 and I3 are equal to, but we do know how we can substitute them in terms of I1, because you can see here in both of these equations, we solve in terms, we have I1 here. So that means we need to do these substitutions for I1. So starting with that, this equation up here, we're going to get the I2 isolated to one side so we can solve for it, right? So I'm going to do a little like semicolon here. I'm going to say 5I2 is equal to 7 plus 10 I1. Solve for I2. I2 is equal to 1.4 plus 2 I1. Okay, so now we have something we can plug in for I2 that's in terms of I1. Now we have to do the same thing for I3. We're going to get I3 to one side, so we're just going to, add 10 I3 to the other side. Left with that 18 minus 10 I1, divide both sides by 10. I3 is equal to 1.8 minus I1. And now we have what I3 is, but in terms of I1, so we can just plug in here. We're now just going to combine all those equations, and it's going to look something like this. So we'll say 0 is going to be equal to I1 plus 1.4 plus 2I1, and then minus 1.8 plus I1. Now we can see we just did the substitution. Everything's in terms of I1. Clean this up and you solve for what I1 is equal to. So I1 is equal to that 0.1 amps. And it came out positive. So therefore our guess that I1 is going counterclockwise, the current that is, it is correct. So now knowing I1, you can just plug this guy into each of these equations like this and solve for I2 and I3. I'm just going to jump ahead here and say that I2 is equal to 1.6 amps. Again, positive, our guess was right. And then this I3 is equal to 1.7 amps. And let's just say I3, this is, fake right here. I'm going to do it in orange. Let's say I3 came out to be equal to a negative 1.7 amps. We can just say like negative, we say like guess is wrong. I3 equals 1.7 amps. And since we said I3 is going counterclockwise, we'll say clockwise. And that's kind of how you do it. And so that's just if it comes out negative, but here we came out positive, so we're good. Now in part B, we're asked to, what's the potential difference between V and A, right? So we have that final position, A, and that initial position, B. So all you have to do to calculate that, that potential difference between those points is do a partial loop. I think that's one of the quicker ways to do it. So I'll just do a partial loop starting from B and going to A. So just go like this, partial loop. So in that partial loop, going from B to A, we'll say that, VA minus VB. And then we just do the same logic we applied. So our partial loop's going the same direction as I2, so therefore minus 5I2. And then we're going to go through the battery, first the minus terminal, then the plus terminal, like this. So that's why it's plus 15. And then we'll say plus 15. We already solved for what I2 is, so we've got to bring that down. And that comes out to be equal to 7 volts. So that's part B. Oh, I should say it's part A. Okay. Now, part C is where it gets a little bit complicated. So what we're going to do here, I think I'll redraw. Yeah, I'll redraw it. I think it'll be helpful to see. So part C where it gets a little complicated. This is a Kirchhoff that now includes a capacitor between these 2 points. So that makes it a little bit tricky and typically not something that you'll see like on the exam, but I think that it's just really good practice because if you do it, if you solve with the capacitor, you know how to do it, you're basically bulletproof on how to do this. If I ever miss something when I'm drawing one of these, just let me know because I sometimes do. Okay. 8 volts, 8 ohms, 2 ohms, 15 volts, 5 ohms. And we'll just call this point B and point A, right, as labeled up here. It doesn't really matter. Like we can say big V is here, it's here, it's here. As long as it's between this resistor and this resistor, we're good. So we know where it is now. So with solving these capacitors, you basically have to make a guess because these capacitors are basically storing, not basically, what they do is they store the charge. So they're kind of acting like a little battery. And what you have to do is just guess which is the plus and which is the minus terminals. Purely just, you flip the coin, right? So I'm flipping a coin and I know which one it is. So I'm going to write it the right way. But, like I said, you have a 50% chance to get it. I'm going to call that the plus terminal and that the minus terminal. This is my guess. Say it's my guess, right? So I don't know for sure yet. And now I just do another loop. Again, I like to do my loop the same direction as the battery goes. So I'm gonna call this loop 4. So, since my battery is going minus to plus here, I do my loop that same way. So the current's going to be going this way, and my loop's going to be going the same way as the biggest battery. So I have 15 volts. I have everything else labeled. So I can now draw for loop 4, starting behind the battery. So it's going the same way. So plus 15. What happens next is we hit that capacitor. Because we hit the plus terminal right with the loop. The loop's going this way. We hit the plus terminal first, so minus Q over C. If we hit the minus terminal first, like if we did our guess the other way, right? We said this was the minus terminal and this was the positive terminal, then we would have plus Q over C. But no, we have our loop going this way and it's hitting the plus terminal first, then the minus, so minus Q over C. Move it on along here. We're going like this through our loop. And now, we already talked about how we defined, what current was this? That was I2 going this way. So that's going through the 5 ohm, the same direction as our loop. So minus 5I2. And what we're looking to solve for is Q, right? So we're going to get QC to isolate it to one side. Q over C. 15 minus 5. We already know what I2 is, 1.6. And all we have to do is multiply by C. So Q equals C times 15 minus 5 times 1.6. And I'll let you plug it in. But just look, well, I shouldn't say that. I know that this is going to be the right guess, right? And your answer is going to come out as some positive value. So Q equals positive, and I'll just call it X. And because it's positive, therefore my guess is good. The positive terminal, I'll say, so therefore, positive terminal is closer to point A. My value came out positive, therefore my guess that that's the positive side of the capacitor is right. Okay, I'm going to pause the recording and take questions. Oh, was that it for this question? Yeah, pausing the recording now. All right, so now we're doing question number 5 here. And this one's just a little bit tricky, but if we're like doing this stepwise, I think we'll be all right. So we want to first work with what is the potential difference between points A and B when the switch is open. Okay, so we can solve this many ways. I think doing partial loops on these kind of questions is easiest, but let's just first off talk about what I wrote here. So here we have, they just draw this gap. It's for me easier to visualize if I have a battery there, so I just write that in. And with these partial loops, we have a ground. This symbol right here means like ground, and this is, what our electrical outlets are plugged into. Is like a copper rod that goes in the ground. And you can always start a loop from a ground going towards where we're interested, right? So we want to know VA minus VB, but we can just find the potential at A and then B doing these two partial loops. But to do that, we're going to need to figure out some things, that being the currents here, right? The current and the charge for that matter. So when the switch is open, it's effectively like it's not even there. So what's the relationship between these circuit elements? Is that they're both in series, right? So they're both in series. So if we were to just simplify everything here, I'm going to say my capacitors in series. What do we do when we have two capacitors in series? We do that inverse addition, and that comes out to be 4 over 3 microfarad. And then with the resistors, we can just simply add. So RS is equal to 12 plus 6, so 18 ohms. Okay, so now we have the REQ and the CEQ. And to do our partial loops, we're going to need to comment on the current, and we're going to need to comment on the charge there. So we need to first solve for those values. So we know how to solve for current. That's just V equals IR. But since we have REQ, I'm going to solve for IEQ. And then we can just relocate REQ like this. That's how we solve for IEQ. IEQ equals 4 over 3 amps. Okay. And then we want to solve for that QEQ. We just have to use Q is equal to CV. You know what we got to plug in. We have that 4 over 3 times 24. And then QEQ is going to be equal to 32 microcoulomb. Okay, we have a little bit of information now. So with respect to each other, they're both in series. So that means we can solve. So that means the charge here is the same thing as the charge here. And then that means the current here is the same thing as the current here, right? They're both in series. So resistors in series have the same current. Capacitors in series have the same charge. Whenever they're in pair, actually, I'll get to that later. So yeah, same current, same charge. Okay, so we can now do our partial loops. So starting from the ground, I can hit A, I can hit B, and I'll call this 1 and 2. So with 1, we're going to be going, up through it. So VA is going to be equal to 12 IEQ. That means VA is equal to 16 volts. Now for VB, we're going to be going through our capacitor. We're just going to have to guess. I'm going to guess this is the plus terminal and this is the minus terminal. Oh, I wrote loop 1 twice. This is loop 2. So if we're now solving for VB, we guess the terminals there. Since we're hitting the minus first, it's a positive, so Q over C. And then we're just going to plug in what Q is equal to, 32 divided by 4. And VB is going to be equal to 8 volts. We can now just solve for the difference. VA minus VB is equal to 8 volts. Done. Okay. Now in part B, what is the potential of point A with respect to the ground when the switch is open? So that's why I like doing loops starting from the ground, because we already know what that is. VA is equal to 16. All right, so that was pretty easy. And then what is the potential of point B with respect to the ground when the switch is closed? So now the switch is closed. So I'm going to redraw the diagram, but just the relevant parts. So it's like this. Draw like this. Like that. Goes up this way. Through a resistor. Switch closed to point B. Okay? And this is point A. This is the 12 ohm resistor. And if you have a good eye, you can just see that we do that loop again going like this, it's actually equal to VA, right? So VA here, or the loop with respect, I'm sorry, the potential at B when the loop is closed, so VB is equal to 16 volts. And if you didn't believe me, and if you don't believe me, you can just solve for it, right? So VB is going to be equal to 12 times IEQ. We already solved for that. That's 4 over 3. And that comes up to be 16 volts too. But the reason it's 16 is because, getting to A here, we go only through that 12 ohm resistor. With the switch closed, it's just a wire, right? So we still only go through that 12 ohm resistor. So that's kind of the quick way you could have made that to solve for that. And then kind of the hard part of this question is part D. So now we have the switch closed. So instead of redrawing the whole diagram, I'm just going to erase everything here. And I'm just going to put a blue line here to tell us that it's closed. Okay, so what's the relationship here? They're both in parallel. Any of these circuits that are in parallel will always have the same voltage, right? Capacitors in parallel and resistors in parallel both have the same voltage. So how we can solve for this difference in charge is to find the voltage drop acting here. So I solve the voltage drop acting here, and whatever it is here, let's call it V1 and call this V2, will be the same thing here. This will be V1 and this will be V2. Okay, so now all we have to do is solve for V1 and V2. To solve for V1, we'll have to plug in. So V1 is equal to IEQ, and what's and then the 6 ohm resistor that's up there. And then you'll solve for all that. V1 comes out to be equal to 8 volts. And then you can solve for V2. Again, same idea, except we're dealing with the 12 ohm resistor. So R with the 12 ohm resistor, V2 comes out to be equal to 16 volts. And do you know the capacity? or the charges here. Oh yeah, they tell us the charges. And now all we have to do is to find that difference in charges. So Q2 minus Q1, because what we're asked to solve for is how much charge flows through the switch when it's closed, right? So initially when it's open, all the charge will flow down like that, right? There's no way it can go this way. It's as if an open wire, an open switch is like there's nothing even there. But now there's going to be some loss. Some can escape this way. To account for that amount that escapes that way, that'll be the difference of the charge here and the charge here. Again, that accounts for how much is lost going that way. So that's Q2 minus Q1. We know how to solve for that because we know C2 over V2 minus C1 over V1. And that delta Q is equal to 48 microcoulombs. Again, we're asked to find how much charge flows through the switch after it's closed. What we need to do is, recognize that here the voltage drop will be the same as here, and then the same can be said about these two. And then the charge here minus the charge here equals how much is able to escape going that way. And then that's how you just solve for the difference. All right, so now looking at question number 6, we have this RC circuit. That means it's just there's resistors and capacitors here. It's initially open and uncharged. So after it's closed, what is the maximum charge on the capacitor? So Q max, what is it, right? Well, part 1, Q max is always equal to QEQ. And then we can just plug in what CEQ is equal to times V. There's only one capacitor, so you only got to worry about the one guy. We know what the voltage is, so that's just equal to 240. Well, that part's pretty easy. And then how long does it take for the capacitor to be 30% charged? So this is a special equation where it's like when you're dealing with a charging or discharging capacitor, there's two sets of equations. Let me look at the formula sheet. I'll pause the recording to see if that's included. If not, I'll add. All right, he did get the last semester they didn't, so I just wanted to make sure you have it this time. So we have RC circuits. We have these voltages as a function of time and like how things charge. So what they have on the formula sheet is this. Okay. And then RC is also sometimes equal to tau. So you can see it written like that. Okay, so in case that comes up. Depending on what we're dealing with here, we can be dealing with a capacitor. So we would just label it like with the VC there. We'd be dealing with a resistor, or we can, like we are in this case, dealing with a capacitor. So you just got to clean up this guy, put a little Q here, let's call it QC, that's what it is. Like that's the max times 30%, which is going to be how long it takes to get to the 30% of the max. And you can use this equation, right? So remember that this equation can go multiple different ways. Basically, when it's in this orientation, it's the charge across the capacitor. Okay, so what we're looking for is when we're at 30% of the max, right? So 0.3 Q max. And what's that Q naught equal to? Again, that's another way of just saying Q max. So you'll see if you have a good eye now that we're just going to be able to do some cancellations here. We can get rid of this Q max and this Q max. What we're left with is 0.3, which is equal to 1 minus this E times T divided by RC, like this. And at this point, we're just going to have to do some cleaning up here. So I'm going to subtract 1, get the minus 0.7 on this side. I'm going to cancel out the negative. So I have 0.7 is equal to E minus T divided by RC. I'm going to natural log both sides to get rid of the E. Left with this. Okay. And then just move RC to the other side. Put the minus here too. Solve for T. And the rest is just plugging everything in and using your calculator. Because they give you the resistance, they give you the capacitance, plug it into your calculator, solve for T. And you guys can do that. It'll be a really small value. These things charge really fast. Okay. All right, we're now continuing with question number 3 here. This one is a little bit tricky, but I think once you see how I kind of take my work, how I work through it, it's going to be just this methodology you could apply on your own. So I'm going to write 3 things here. 1, 2, and 3. We know that the current is going to be entering through A and leaving through B, and it's going to go through this complex resistor looking system, right? So if you imagine when it first comes in, it's going to hit this point and it has 3 different options of where it can go. It can go this way, it can go this way, or it can go this way. So these ones, I'm just going to like put a little red mark here, a little red circle here on all of these guys. How many red circles do I see? I see 1, 2, 3. And then I kind of ignore the complicated middle and I look at the exit. To exit, all these resistors are going to be hit at the same time, and it's going to go out like this. So I'm going to put these little, I don't know, is this green, blue, over here. And then in between, each one of these resistors is going to be hit at the same time, because by definition, between all of them is a junction point and then the subsequent resistor. Junction point, subsequent resistors. Junction point, subsequent resistors, right? So with this, with all these other guys, I'm going to do these blue circles. Count of my blue circles, there's 6. Okay? So I kind of chose my words there carefully, and I said between them, there are these junction points right here, 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 and here. So being all separated by junctions, relative to their color, they're all in parallel. So if we're to draw this now in a 2D plane, this is point A, what we're going to do is hit all these. I'm just going to like literally draw the worst resistors ever. All those reds. So this constitutes 1. And then it's going to hit the second junction, and it's going to hit all those blues, 6. So 1, 2, 3, 4, 5, 6. Call this 2. Continue along. And then we're going to hit this 3. And I think with this one, it's easiest to work from the starting and the end, and then work backwards into the middle, because you'll see that they're all going to be hit at the same time by that. So that's kind of how I imagine it. There's that junction that separates them. I keep saying it like it's hit at the same time, but like you'll see it's a repeated pattern of, it first only can go these 3 ways. And then between all those 3 ways, there's always going to be a junction followed by the resistor in which it interacts. Junction and followed by the resistor in which it interacts. And then same thing, junction, resistors that interacts. That constitutes the 2s. And then close out, it can all go that one way. So, yeah.
So once you calculate like 1